So the idea here is that this represents a tall building and this represents a short building. And we thought maybe the higher the frequency of the earthquake, we wanted to see, you know, the difference between the two structures. So if it has a low frequency, it's going to shake this building more than this building. So we'll test it out. So this is a low frequency earthquake here. You can see that that tall building is swaying and not much is happening to the short building. If it's high frequency, that means it goes faster. Hold on.
Yeah. It's easier, yeah.
You can see that the short one is shaking a lot more than the tall one. So what we came up with was something, we wanted to test this to see if we can make a building more structurally sound. So, Samantha, do you want to see what we did? Sure. So over here, I think we did this one. We created a tall structure, tall building, and a short structure. And then to verify that the earthquake affects the two different buildings differently, or the two different frequencies, we're going to demonstrate this on a shake table.
Do you want to take them or not?
Oh,
Yeah.
we were going to play.
As long as no one's staying behind it.
So we're just going to stabilize the base of the building to the shake table. So you can see at a low frequency, the taller building is shaking more than the short building. And if we go to a high frequency earthquake, you can see that the shorter building is showing more shake. So that just verifies that high frequency earthquakes have more effect on short buildings, and the low frequency earthquakes have a higher or bigger effect on the tall buildings.
So, yeah, you're fine. So as you can see here, on some of these buildings in other cities like Chicago and just in Japan, they've done things such as bracing to stabilize taller buildings at lower frequency earthquakes. So we wanted to test how that would work with an equivalent structure, but only with bracing. So we did that. What we could put these guys on. And these can simulate. Whoops. Yeah. Oh yeah. So that simulates just any piece of furniture in the house. No, it's good.
I'm going to take this.
Okay. So let's see what happens at low frequency and high frequency. So as you can tell, low frequency, this one's shaking a lot more without the bracing. And at high frequency, this one's still shaking. Yeah, but it's more pronounced at lower frequencies. How much difference the bracing makes.
Good.
Cool.
Our houses are all attached to the ground.
Yeah.
But, so therefore, if the ground shakes, one would imagine that the building on top of it will shake. So the question is there any way we can separate the building from the ground? And there is a technique called base isolation. And this is one model for it. And we will see how much the ground is moving and how much the building is moving. So if you kind of tape it from that angle, focusing in here as well as the building, you can see this will be going back and forth because it's attached to the ground and the structure will not be. Okay. You may want to hold on to that, Lillian, if
I
it
think
starts falling
last
down.
time Samantha was like putting her finger
Right here?
Yeah.
just
On
like
the
at
base.
base.
Oh, okay.
And Megan, you want to go immediately to about 30 or so high frequency.
Okay.
Just for your information, these are the type of things that they are using in Japan. Either suspensions attached to the ground, the building is above that, or lead core with rubber rings around it. So when the ground moves, the bottom is going back and forth, but the top is stable. So here, the bottom is going back and forth, building is stable. But if the building is attached to the ground, the building is going to sway, as we have seen. All right.
That's all their structures.
Right. Now we go to liquefaction. Check that thing.
Am I in your way? I can-
No, I'm trying to stay out of your way.
No, you're not in my
I
way.
can put the tapes on it if you want.
Oh, okay. You can take it. Are we gonna need more water?
Where's that
Where's that
watering
water? Yeah.
can?
Get dry. Yeah.
Yeah.
Oh, we did the brick house.
Give me that one here. Oh, we did the, yeah.
And here's the screw, if you want to
Let's see that.
see it.
So Sarah, you gonna talk about this one?
Yeah.
And
Yeah.
somebody has to mix it. Yeah. So now we're testing liquefaction, which is when buildings are on top of things like sand, or we did a lot of different things on the bottom. So like rocks, this is sand with rocks mixed in, and then this is soil. And when these things get wet and the ground shakes, the particles at first are close together when they're dry, and then wet, and then when the ground starts to shake, the particles actually separate and water rises to the top and the particles sink down, so then the building ends up being on water and will fall over or float away or things like that. So we thought that we would test a lot of different bases and then see which one worked the best. So we're going to use sand as an example.
And right behind you, there's some great pictures showing the effects of liquefaction, real life circumstances. Should we add more water?
You can add a little bit more, but not too much. Where are the buildings?
Did
We wanna
we,
Oh,
use,
I see.
should we use both of these or just one at first?
But doesn't matter. You can just work it out. That seems to be good. Something just roughly level the surface a little bit. Not too much, but yeah. So it's water saturated ground.
So the blue top is going to act as our
Yeah,
smaller
good.
building, and the orange
That's good.
reddish
That's
top
good.
will act as our tall building. And we will see what happens.
Yeah, good.
Let's see. Yeah. taller building is already shaking and the shorter building is pretty steady right now. And at higher frequency, the taller building is at a 45-degree angle moving down.
See, the water's rising a lot more than this time.
You go higher or?
I don't think anything's gonna happen.
So we might have also, we did lower these quite a bit also into the soil, but.
Yeah.
What did you say about the water?
I was just saying the water level came up a lot from the earthquake, so that's causing the houses to not be as stable.
So what we are seeing here is similar to this picture. The building is leaning over. So let's mix it up again and then put that four-legged stuff. Oh, but we need to this has a flat regular foundation, but this thing has piles and going quite a bit down. Yeah. So let's see how these two buildings with piles, without piles will behave.
So at low frequency, the tall building is already falling, it's on a flat base. And nothing is happening to the one on piles. And at high frequency, nothing's happening to the one on piles. It's still barely even shaking.
So this suggests that buildings that have the concrete piles built down into the bedrock will be more stable than a flat base foundation.
Next time I was thinking maybe we should tape this on top of that. Yeah, to show
Should tape
this.
it on top of that?
Yeah, we can do it now, it's wet, but or we can build another one, tape it, to show that that will stand and this is going to lean over.
Right. That's a good idea.
Okay?
And we did tests, as Sarah was saying, in different types of soil with liquefaction also.
And the one with the sand and the rocks mixed together proved to be the best or stronger, so the building stood for longer periods of time without falling over.
All right.